All right, so this is 8-2, angle bisectors of triangles. So I'll be walking you through the homework and talking about angle bisectors. Before we get into that, let's just talk about what angle bisectors are. So you should be familiar with them from before. Here's an angle. And an angle bisector is a segment or line or ray that cuts that angle into two equal pieces. So that right there, that green part, is an angle bisector because it fits the definition. We've got an angle that's cut into two equal pieces. So when it comes to angle bisectors of triangles, here's a triangle. Triangles are named for their angles. There's three of them, triangles. So we're going to have three angle bisectors. So this one, I'm just eyeballing, looks to be about there. It cuts this angle into two equal pieces, whereas this one looks to be sort of here-ish. So there. And notice I'm not saying that this angle here is equal to this angle. It cuts this one into two equal pieces. So if this angle right here were 30, that would be 15 and 15. And if this angle down here, which looks bigger, maybe it was 50, it'd be 25 and 25 here. So our last angle bisector is going to go from this vertice off, and if I do it right, because I'm kind of just eyeballing this, sort of got it bisected. And then 1, 2, 3. So those two angles are going to be equal because those are all angle bisectors. And you'll notice that the angle bisectors intersect at a point, just like all of our special segments and lines and triangles do. And this point we call the incenter. So that point inside there is the incenter. These are angle bisectors 1, 2, and 3. They go from a vertex and they cut the angle in half. That's why they're called bisectors, right? Bisection. And the center, that part in there, is called the incenter because that is the center of a circle that perfectly fits inside this triangle. And I know my drawing's pretty bad. It doesn't look like it perfectly fits. But it's the center of a circle that fits inside the triangle, that hits each side of the triangle only at one point. So it's the biggest circle you can fit inside the triangle before it just barely kisses each side, touching it at one point. The word we use is tangent for that. When something is tangent, it means it just barely touches it at one point. So if you can imagine when you have a surface, like a floor or a table, and then you have some kind of ball that sits on it, that ball is not laying flat on there. It's actually just barely touching that surface at one point because the rest of it's curved, and so it's not touching here, here, here. It's only touching at one point, and so we call that tangent. Where a line is tangent to a circle, it is touching the circle at one point exactly, and just one point. If the line was touching it at 2 points, then it would be going through the circle. So that is not tangent. This is. And so this circle is tangent to this line, and this line. It's the biggest possible circle we can fit. And what's cool about that is that any line that goes from the incenter to the outside of that circle, or especially to the outside of these triangles, they're all going to be the same length because they're all radiuses, or radii. So all the red parts are radii, and so all of those red lines, in theory, if I drew this correctly, would be of equal length. So there's some cool properties of that. I'll show you that next. So if we have a triangle, and I tell you that these are angle bisectors, here, here, and here. So angle bisectors just like we had before. Then you would know that this point right here in the middle, where they intersect, is called the incenter. And so if I gave you all that information and I asked, hey, what is the measure of this part right here, from there to there? You would be able to figure that out because you know that's a radius. So anytime I draw a line from here to here, from the incenter to the edge of a triangle, I know that those are all going to be congruent. They're all going to be the same length. So if I told you, as an example, that this length right here was 3 inches, and I asked you, okay, well, what's the length of this one? Well, you would know that this is also 3 3 inches because these red lines are all radii of a circle centered at the incenter. So let's get into the homework. Alrighty. So for 1 through 4, we're using this figure over here, and it says, let me zoom in a little bit, it says, given that FG and GH are equal. So FG and GH are equal for this example, although we're going to need to use the same triangle, I think, for multiple examples. So let me draw that figure so we can put our markings on it without ruining it for the other examples. I hate when the book does that. All right, so for this example, we've got F, G, and H, and they tell us this is 90 here and here, and they tell us this is J, and this is, what is it, K? K and E, yep. All right, so here's this, and it says in the instructions for number 1, they give you that FG and HG are the same. So let's mark that on our diagram. FG and HG are congruent, so I did that. And it also tells you that FEH is 55 degrees. So let's mark that. FEH is this big angle right here. FEH, so that angle is 55 degrees. And they want us to find GEH. So measure of angle GEH equals what? So because we know that this right here and this over here are equidistant, or I should say are congruent, we know that this point right here is equidistant from 2 sides of the triangle. Now what's cool about angle bisectors is that when we have 2 segments here equal, we know that this line right here is an angle bisector. So that means that this line splits up this big angle right here into 2 equal parts. We know that because this point is the same distance from both sides of the angle. Here's our big angle. It's the same distance from this side of the angle and this side of the angle. So therefore, this right here is an angle bisector. So it cuts this green angle into 2 equal pieces. So when they ask GEH, what measure is that? GEH is this one right here. Well, it's going to be half of 55, which is 22.5 degrees. So again, walking you through it, the idea here is that if you have an angle, and you've got a line or something in between it, any point on that line, I'm going to choose this point randomly. If this is an angle bisector, which I told you it is, right? We've got our angle bisector, and I pick a point on that angle bisector, I know through the angle bisector theorem that that point is going to be equidistant from both sides of the angle. And the reverse is true. So before I said, hey, this is an angle bisector, and then I was able to show angle bisector theorem says these 2 are going to be equal, right? The reverse is also true. So if I have this, and all I know is that random point on here, I know it doesn't look like it, but trust me, is the same distance from both sides, right? I told you they're both the same. Then I know for a fact that this and this are the same angle. Love that bell. Love that bell. So here I noticed that they gave us these 2 are the same. So if those 2 are the same, this is an angle bisector, so I know these 2 are the same. So same sides, same angles here. So that means if this guy's 55, the little guy is 22 and a half. So let's use the same diagram again for our next one. So it looks something like this, I think. And it was F, G, H, and K, J, and E. And they gave us this. All right, so for this one it says, given that EG bisects FEH. So EG, that's going to be this part right here, bisects FEH. So this guy is bisecting this angle. Well, if he's bisecting that angle, then we get this, right? That's what a bisector is. This guy is bisecting this angle. So they also tell us that GF is root 2. So this length right here is root 2, which is just a number. And it says to find GH. So GH is our question mark here. GH, the measure of that segment, is what? Well, GH is this segment right here. That's the segment we're talking about. So we want to find the length of that. Well, just like I said earlier, if we know that this is an angle bisector, that means that this point, any point on the angle bisector, including this point right here, is going to be the same distance from both sides. So if this is root 2, this one must also be root 2. We knew that because these two angles are equal, so these two sides here are equal. Same diagram for number 3. This was F, this was G, this was H, this was J, K, and E. And again, they gave us that these are two 90-degree angles. That's important because when we measure a distance from a point to a side, we always want to go at 90 degrees. We don't want to measure the distance here, right? That's how we can guarantee that we're measuring the same distance both ways. So number 3 says, given that FEG is congruent to GEH. So FEG is congruent to GEH. So it's saying these two angles are congruent. Okay, so that looks very similar to what we had before. This angle and this angle are congruent. And then it also says that FG is 10z minus 30. So FG is this part right here, 10z minus 30. So I'm going to write that in. So that's 10z minus 30. And it also tells us that HG is 7z plus 6. So HG is this part. Okay, so we get the other part, this part right here. And they said it was, what was it, 7z plus 6. And it wants us to find FG. So FG equals what? So we want to find the length of this. Well, just like before, we know that because these two are equal, this is an angle bisector, right? So these two are equal. So that means these two sides are equal. So if they're equal, write that. 10z minus 30 is this side, right? And that's going to equal this side, which is 7z plus 6. And now we're just going to do math to solve for z. So first step is I'm going to add my 30 over here. And what I get next is this. 10z equals 7z. That's going to be 36. And then I'm going to do something that's a terrible idea in real life, but a great idea in math. I'm going to get my x's together. So I'm going to move this over with this. And when I do that, I get 3z equals 36. And now, we always save this for last because, you know, division should be your last resort when trying to make a better world. We're going to divide by 3 to both sides to separate the 3 from the z. So we get z, because the 3 has been separated, moved over here. 36 divided by 3 is going to be 12. So z is 12. Well, if z is 12, and we want to find fg, 10 times z minus 30 is fg. So it's going to be 10 times 12 minus 30, because the z is 12. So we get 120 minus 30, and that's going to be 90. So z, fg is 90, maybe 90 inches, 90 feet, I don't know, something like that. So fg is 90. Looking at number 4, we have the same diagram, so I'll draw that up. Number 4 is this one. F, G, H, 90, 90, J, K, E. All right, so they tell us in this one, given that GF and GH are congruent, so GF and GH are congruent, and measure of angle GEF is 8/3 A. So GEF is this one, GEF. So that angle right there is 8/3 of A degrees. It says, and GEH is this one right here, it's 24. This angle right here, let's do it in pink. GEH, this angle right here, is 24 degrees. And they want us to find the measure of A, so they want us to find this value right here. Okay, not any angle or segment on here. It's just what is that variable. So we're just solving for that variable. Well, we know that since these two are equal, this is an angle bisector. And so these two angles are equal. If those two angles are equal, write that. These two angles, this one, should be equal to the other one, which is 24. So now we want to solve for A. And the way we do this is with algebra. Uh-oh, I froze up. All right, there we go. So the way we do this is with algebra. So in order to separate the 8/3 from the A, because I have nothing left to do, it's time to divide, I need to divide by 8/3. But we don't like dividing by fractions, so what we do instead is we multiply by the reciprocal. It's the same thing as dividing. As long as you flip it, you can change it from division to multiplication and it works out. So I'm going to do this. So when I do this, I get 3 times 8 over 8 times 3. Well, it's going to be the same thing over itself, right? So it's going to be 1, so it goes away and we get A. That's the whole point of multiplying by the reciprocal. We get 24 on top and 24 on the bottom. 24 over 24 is just 1, so it's 1A, which is just A. Over here, now we have an option. We can multiply by the top times 3 and then divide by 8, or we can divide by 8 first and then times by 3. You could have also done this and then just multiplied across, but this is going to help you not have to do as much work. So let's, instead of making the number really big, let's divide by the bottom, because I know 24 divided by 8, and that's 3. So I get 24 divided by 8, and it's 3, and then I times by the top. So I took 3 here, and I times by the top and make it 9. So A is 9. If that's confusing you, here's another way that might help. Okay, so if you don't like that, ignore it. Let's start with the same problem. Remember, fractions are just division for lazy people. So in order to get rid of that divides by 3, I'm going to multiply by 3 to both sides. So that gets rid of the divides by 3 and leaves me with 8A equals 24 times 3, which, trust me on this one, 72. 20 times 3 is 60, 4 times 3 is 12, you add them together, 72. And then our last step is to divide by 8 to both sides, to separate the 8 from the A. So in order to get rid of that first division, you got to multiply. And then when you're here, it kind of looks like any other problem, right? You got to divide to separate the 8 from the A. So looks weird, and then once you do that first step, it's not so bad. It's like a problem you're used to. So then we get A equals 72 divided by A, which is going to be 9, just like we said before. So A is 9, and that's the answer for number 4 on the worksheet. Taking a look at 5 through 9, we've got this diagram right here, and we can use that diagram for all of this. So let me zoom in just a little. Let's zoom out a little. All right, so use this figure. It tells you that GJ and IJ are angle bisectors. So let's find those right now. GJ right here and IJ are angle bisectors, which means that this angle here and here are equal, and this angle here and here are equal. So we know that. And then it says find each measure. So I'm going to zoom in on that triangle, and I'll read you what the first one, or number 5 says. So number 5 is looking for angle JGK. So we have JGK. So we're looking for this angle right here, JGK. Well, we know that this angle here is 23, right? It says so, this part. So if that's 23, this must be 23. So that's 23 degrees for number 5. Taking a look at 6, JIK. We want to find that measure. So JIK. Well, same idea applies. These two are equal. So if we knew that the angle measure of this one or this one, we could do it like we did last time, right? But we don't know that. This is actually referring to this length right here. So that 82.1 is how long that is. Okay, so we don't know the angle measure here. But we can figure it out. We said this one's 23, right? We did that in our last problem. And so 23 and 23 makes 46. So this is a 46 degree angle right here altogether. And this is a 26 degree angle. Well, the interior angles of a triangle always add up to 180. So if I do 180 minus 46 minus 26, I should get this big angle right here. Well, those put together is going to be 72. So when I subtract 72, I get 108. So that whole angle is 108. So how much is half of that angle? This part right here, the part I'm interested in? Well, it's going to be half of 108. Well, half of 108 is 54. So this angle right here is 54 degrees. And so is this one. Next, they want to know about angle KJI. So KJI, this angle right here. Well, if you're clever, you'll notice that this angle down here is also 90 because it's a linear pair with this one. They're both angles on a line, those two angles. So if that's 90 and that's 54, we can solve for this one. So 90 plus 54 is 144, and they should add up to 180. So that angle right there is going to be 36. So again, I did that by knowing that this was 90, and this has to be 90 as well because it's a linear pair. They're both on the same line. So that guy's 90, that guy's 54. If I add 90 and 54 together, I get 144. And then I subtract that from 180, and I get 36, which is this angle right here. Now we want to do the distance from J to GH. So here's J, and GH is here. So the distance from J to this line segment. Well, remember earlier I said whenever we do distance, we want to do it at a 90-degree angle. So from J, 90-degree angle to here. So what's the distance there is what they're asking. What's that distance? Well, what's cool is that this is an angle bisector, and so is this, right? They told us that in the original problem. GJ and IJ are angle bisectors. So they intersect here. So right here is the intersection of angle bisectors. J is the intersection of two angle bisectors. So J, if you remember from before, is our incenter. J is an incenter. And what's cool about incenters is that they represent the center of a circle that you could draw inside of here that hits every side at one perfect point. So you'll notice that this part right here, the part they're asking about, is a radius. It's a radius of this circle. So any line from J to the circle is going to be a radius. So J to K is a radius, and they told us that that is 64.3. So if this radius is 64.3, then this radius is 64.3. 64.3 is the distance, not an angle measure. So that's how long that is. Now you might be asking, wait a minute, I thought you said any line from the incenter to the circle is 64.3. Well, that makes sense here and here. But why is this guy not 64.3 then? He says he's 82.1. Well, if you're careful, you'll notice that the circle doesn't go all the way down to here. It comes in a little bit. So 82.1 is just a little bit longer than this piece right here. This piece right here is a radius. But as soon as we go further, it's going to be 82.1, which is not a radius. Last one is the distance from J to IH. So from J again, and we're going to IH. Well, if we're going to IH, we want to go at a 90-degree angle. And it turns out, going to that 90-degree angle is exactly where this circle is going to kiss, right? It's going to be tangent. That's always true for any tangent circle. So like when I did this earlier, lots of colors. So when I drew this thing earlier, right, this circle is tangent to this line. Turns out that the intersection between those two is at a 90 degree. And that's always true. It's going to be a straight line down. That's where that point is. So from here to here is 90, and that's where it hits. So this is a radius as well. From J to IH, because we're measuring the distance between them. Probably 90 would be closer to over here than it would be this one, so my sketch is a little off, but right there would be another radius of the circle, so it would be 64.3. Last one. Raleigh designs the interior of cars. A triangle surface shown in the figure is molded into the driver's side door as an armrest, so that's an armrest. It's an above view. Raleigh thinks he can fit a cup holder into the triangle, but he'll have to put the largest possible circle in the triangle. Explain how he can do it. Well, at the intersection of the angle bisectors will be the incenter, right? And the incenter is the center of the circle that just barely fits inside that triangle. It's the biggest possible circle. So how can we find where the cup holder should go to be the biggest? Well, we need to do the angle bisectors of this thing. So that looks like it's about cutting this in half. And this one right here looks like it's cutting it in half. And then I'm going to cheat a little bit. I know they have to intersect. there is an angle bisector. Not too bad. So the point where they all intersect is the center of that circle, the circle we're looking for. And if we draw that circle, which I did pretty poorly, that incenter is not perfect, then we should get the biggest possible circle that fits inside this armrest, the biggest cup holder. So how can he do it? Raleigh can find the intersections, find the intersection of the angle bisectors. And then use a compass to draw a circle centered at the incenter and touches the sides of the triangle. So what he would do in practice is he would find the center, finding the angle bisectors, maybe use like a protractor to make sure that cuts it in half perfectly, and then he would take his compass and he would put it on the center here, that incenter, and then he would find the point where it barely touches the outside, and then he would trace his circle. And when he traced his circle, he'd get something that looks like this, probably a prettier one if he's using a compass, and it would be perfectly just touching each side. So as big as possible without breaking outside of that armrest. So that's 8-2, the important concepts. Just to summarize, we have angle bisectors. It's something that cuts an angle into two pieces. That's why it's called an angle bisector. The intersection of the angle bisectors is here, the incenter, and the incenter is the center of a circle that just barely fits inside the triangle. It's tangent to the sides of the triangle, so that circle touches each side at one specific point, here, here, and here on my diagram. And what's cool is that any line from the incenter to the edge of the circle is going to be a radius, so all of those red lines in there are equal length. I showed you another example down here. So if this is 3 inches, well then that means this red line is 3 inches because it's from the incenter to the edge of the circle, and so is this one. So those are radii. The last important thing is we have angle bisector theorem. Let me write it officially. THM. And the idea is that if we have an angle, if you have an angle, and there's a ray in between them, any point on that ray, so any point I choose, like this one right here, and I told you this was an angle bisector, right? So if you have an angle bisector, any point on the bisector will be the same distance from both sides of the ray, both sides of the angle at a 90 degree. So those two will also be equal. And the reverse is true. If you're given an angle and it's got a line going through it, like this, and they tell you that there's a point on this line that is the same distance from both sides at a 90 degree. So if they give you this, then you know that that green line right there, that green ray, is an angle bisector. So one implies the other. Angle bisector means that any point on it is the same distance from both sides of the angle. Same distance from both sides. Distance there, distance there. And if we have a point on a line that's the same distance from both sides of an angle, then we know that that line must be an angle bisector. So those are the big points in this lesson. Hopefully you did all right in the homework and understood it. Best of luck on exam.